Hello everyone, I am Jyoti Bhung, and in today's video we are going to discuss about the compaction of a soil. So first of all we will see what is compaction. So the compaction is nothing but a process by which the soil particles are artificially rearranged and packed together into a state of closer contact. So this can be achieved by the mechanical means in order to decrease the porosity and thereby increase its dry density. So this usually is achieved by the dynamic means such as tamping, rolling or vibration. And here the process of compaction involves the expulsion of air only. So in the natural location and condition, the soil provides the foundation support for many structures. Besides this, soil is also extensively used as a basic material of construction for earth structures such as dams and embankments for highways and airfields. So the general availability and the relatively low cost are the chief causes for using soil as a construction material. The properly placed and compacted, the resulting soil mass has better strength than many natural soil formation, and such soil is referred as a compacted earth fill or a structural earth fill. Okay, so for the purpose of supporting highways or buildings or for other retaining water, as in earth dams, the soil material must possess certain properties while in place. And these desirable features can be achieved by proper placement of an appropriate soil material. The most of these desirable qualities are associated with high unit weight or dry density, which may be achieved by the compaction. So virtually any soil can be used for the structural fill if it does not contain organic matter. Okay, so the granular soils are capable of achieving high strength with relatively low volume changes, whereas poorly compacted clay soils will develop relatively high strength and low permeabilities, which may be desirable features for earthen dams. So we will see what are the purposes of compacting a soil. So when we compact a soil, we will get the increased shear strength of the particular soil mass. We will get reduced permeability, reduced compressibility. Then we will get the control on swelling and shrinkage property of a soil mass, and there will be a reduction into the liquefaction potential. So these are the various purposes of compacting a soil sample or a soil mass. So now we will see about the principle of compaction. Okay, so the process of compaction is accompanied by the expulsion of air only, as we have already seen. Okay, so in practice, soils of medium cohesion are compacted by means of rolling, while cohesionless soils are most effectively compacted by vibration. So prior to the advent of rolling equipment, earth fills were usually allowed to settle over a period of years under their own weight before the pavement or other construction was placed. The degree of compaction of a soil is characterized by its dry density, and the degree of compaction depends upon the moisture content, the amount of compactive effort or the amount of compactive energy expended, and the nature of the soil. So a change in moisture content or compactive effort or compactive energy brings about a change in density. Therefore, the compaction of a soil, a certain amount of water and a certain predetermined amount of rolling are necessary. Okay, so here we can see in the diagrams over here the diagrams of soil particles before compaction and after compaction. Here also we can see the before compaction and after compaction. So from the images we can clearly see that there is the we can see before the percentage of voids, the presence of voids before the compaction, and here we can see the voids are lesser as compared to the previous one. Okay, so the compaction of soil is achieved by reducing the volume of voids, and it is assumed that the compaction process does not decrease the volume of solids or soil grains. Also here we can see the diagrammatic representation of a compaction effect. So here we can see in terms of a three-phase soil system. So here we can see this is the soil sample or soil mass having the three different phases, that is solid phase, water phase and air phase. That means there is a presence of air and water in the voids. And when we represent the soil mass diagrammatically in different phases, here we can see the three-phase diagram. That is, the first phase is a solid phase, water phase and air phase. And when this soil, this is the three-phase diagram in soil is a in loose condition, in loose state. And when we compact this soil mass or when we compact this soil sample, here in the second diagram we can see that there is a reduction into the volume of a soil. Okay, here we can see after the compaction, after the sudden application of a load, whatever air is there in between the voids, some of the air will get expelled out and there is a reduction into the volume of a soil mass. So here we can see diagrammatically the compaction effect over here clearly. Now here the degree of compaction of a soil is measured by the dry unit weight of a skeleton, and dry unit weight we can easily find out. We know the formula, that is gamma D is equal to gamma W into GS upon 1 plus E, where gamma D is nothing but the dry unit weight, gamma W is the unit weight of water, GS or G is nothing but the specific gravity, and E is nothing but the void ratio. So the more the compacted the soil, it will be having a smaller void ratio and it will be having a higher dry unit weight. Now we will see about the compaction curve. What is compaction curve? So the relation between moisture content and dry density of a soil at a particular compaction energy or at a particular compactive effort is shown here over here in this diagram. Okay, so the addition of water through a dry soil helps in bringing the solid particles together by coating them with thin film of water. And at low water content, the soil is stiff and it is difficult to pack it together. And as the water content is increased, water starts acting as a lubricant. The particle starts coming closer due to increased workability, and under a given amount of compactive effort, the soil water air mixture starts occupying less volume, therefore effecting gradual increase in dry density. And as more and more water is added, a stage is reached when the air content of the soil attains a minimum value, therefore making the dry density a maximum. So the water content corresponding to this maximum dry density is called the optimum moisture content. And the addition of water beyond the optimum reduces the dry density because the extra water starts occupying the space which the soil could not occupy. Okay, here we can see in the diagram, here we can see the compaction curve. Okay, so here we can see at the peak of this curve, so the corresponding dry density at the peak is nothing but the maximum dry density, and corresponding water content is nothing but the maximum water content, or we can call it as a optimum moisture content. And when and also we can see that when we start adding the water beyond this peak, the dry density starts decreasing. Okay, so the curve with the peak shown over here is known as the moisture content dry density curve. This curve here is known as the moisture content dry density curve or the compaction curve. Okay, so the state at the peak is said to be that of 100% compaction at the particular compactive effort over here. Okay, and the curve is usually a hyperbolic form when the points obtained from the test are smoothly joined over here. Okay, the wet density and the moisture content are required in order to calculate the dry density. We have a formula, gamma D is equal to gamma upon 1 plus W. We have another formula also of calculating the dry density, that is gamma D is equal to gamma W into G upon 1 plus E. But generally we prefer this formula, as in the compaction test we can calculate the wet density and we can calculate the moisture content. So it is easier to get the dry density or dry unit weight by using this formula. Optimum moisture content, OMC. Okay, so here in the diagram you can see the OMC. Okay, over here this is the OMC, that is optimum moisture content or maximum water content we can say. So as we have already seen in the previous slide, the water content corresponding to maximum dry density. Okay, here is a peak of this compaction curve. So the water content corresponding to maximum dry density is called as a optimum moisture content, OMC, or we can also call it as a maximum water content. So increase in the compactive effort or energy expanded will result in the increase in the maximum dry density and the corresponding decrease in the optimum moisture content. Here we can see in the diagram. Okay, so here this curve is of a lower compactive effort and this curve is of a higher compactive effort. Okay, therefore the purposes of standardization, especially in the laboratory, the compaction tests are conducted at a certain specific amount of compactive effort expended in a standard manner. Next is a zero air voids curve or a saturation line. Okay, so what is saturation line or what is zero air void line or zero air void curve? So a line showing the relation between water content and dry density at a constant degree of saturation S may be established from this equation. Okay, so it is the line, it is the saturation line is the line which shows the relation between the water content and dry density at a constant degree of saturation, that is at a constant value of S. Okay, and it can be established from the equation. We have this equation, gamma D is equal to G gamma W upon 1 plus W into G upon S. That is gamma D is nothing but the dry unit weight. Here G is nothing but the specific gravity, gamma W is the unit weight of water, W is the water content, G is again specific gravity, and S is the degree of saturation. Okay, now substituting S is equal to 95%, degree of saturation is equal to 95% or 90% or 85%, 80%, so on. So one can arrive at gamma D values for different values of water content in percentage. Okay, so the line therefore obtained on the plot of gamma D versus W are called as 95% saturation line or 90% saturation line or 80% saturation line, etc. Okay, and if one substitutes S is equal to 100%, if we put S degree of saturation is equal to 100% and plots the corresponding line, then one can obtain a theoretical saturation line. Okay, here in the image you can see one can obtain a theoretical saturation line. Why it is called as theoretical saturation line? Because it can never be reached in practice, as it is impossible to expel the pore air completely by compaction. Therefore it is called as a theoretical saturation line. Okay, so here we can put the S is equal to 100% and we will get the theoretical saturation line relating dry density with water content for a soil containing no air voids. Okay, so we can use this formula gamma D for S is equal to 100%. We can use this formula gamma D is equal to G gamma W upon 1 plus W into G, where S we are going to consider as a 100% saturation. Okay, so the saturation lines when superimposed on compaction curve give an indication of the air voids present in different points on these curves. Okay, so now in the next slide we will see the difference between the compaction and consolidation. Okay, so compact in both the cases the volume gets reduced. In both the cases the volume of a soil sample gets reduced, but both these processes are different. Okay, and what is the difference between them, that we will see. So compaction is an instant process. It can be used for all type of soil. Okay, so it is an instant process. The expulsion of air takes place on a sudden application of a load. Okay, it is an instant process and it can be used for all type of soil, whereas consolidation is a slow process and it can be used for only clay type of soil. Okay, in consolidation the expulsion of water takes place. Okay, in compaction the expulsion of air takes place. In consolidation the expulsion of water takes place, and for the expulsion of water the consolidation is a gradual process. It is a slow process. Okay, we need to apply the load which is a gradual and long term. Okay, the next difference is it is a artificial process. The compaction is a artificial process, whereas consolidation is a natural process. Okay, so in compaction the dynamic loads by rapid mechanical methods like tamping, rolling and vibration are applied for a small interval in soil compaction, whereas static and sustained loading is applied for a long interval in soil consolidation. In compaction, soil changes from partially to fully saturated condition, and in consolidation, soil remains in fully saturation condition. Compaction is due to expulsion and compression of air in soil mass under short duration by moving or vibratory loads, whereas in consolidation is due to expulsion of pore water from voids under steady, static, long-term load. The dry density of soil increases, but water content will remain same in case of compaction, and in consolidation the dry density of a soil increases but water content will decrease. Okay, so this is the difference between the compaction and consolidation. Now next we will see the laboratory compaction tests, various laboratory compaction tests. So the compaction characteristics like maximum dry density, optimum moisture content are first determined in the laboratory. It is then specified that the unit weight achieved though compaction in the through the compaction in the field should be a certain high percentage of the laboratory value for quality control of the construction. And the various procedures used in laboratory compaction test involve application of impact loads, kneading, static loads or vibration. And some of those important procedures are standard Proctor test and modified Proctor test. We will see those one by one. So here is the first we are going to discuss about the standard Proctor test. Okay. So first of all, let me clear that in the diagram I have shown the various dimensions of this apparatus, standard Proctor test apparatus. So in some reference books, suppose here the diameter of this mold is given as 101.6 mm, but in some reference books this value is rounded like 102 mm, or here the height is given as 116.4 mm. In some reference books it is given as 117 mm. So I'm going to, while talking, I'm going to give the dimensions as per the given in the reference books. Okay, this is diagram is also from a reference book, but in some reference books the values are rounded. Okay, so we will see about the standard Proctor test. So this test was developed by R. Proctor in 1933 in connection with the construction of dams in California. So the apparatus used for the test consists of a cylindrical mold. Over here we can see it consists of a cylindrical mold of internal diameter 102 mm and an effective height of 117 mm with a volume of a 0.945 liter. Then it consists of a detachable collar. Here you can see a detachable collar is there. So it is having a effective height of 50 mm and a total height of 60 mm. Then a detachable base plate, okay, and a 50 mm diameter metal rammer of weight 25 Newton and a height of fall of 300 mm moving in a metallic outer sleeve. Okay, so this is a diagrammatic representation of a standard Proctor test apparatus, and this is the actual image of a standard Proctor test apparatus. This is the mold, main mold, this is the collar, detachable collar, and this is the detachable base plate, and this is the rammer, or you can also call it as a hammer. Okay, so we will see the test procedure. About 30 Newton of air dried soil passing 20 mm sieve is taken. Okay, then a reasonable amount of water is added to the soil and it is thoroughly mixed. Then the mold is filled with this moist soil in 3 equal layers to give a total compacted depth of 130 mm, and each layer is compacted by giving 25 number of blows. Okay, in this way you have to give the number of blows. In this way you need to cover all the surface area of that particular soil mass with the 25 number of blows. Okay, so we are going to give the 25 blows with the standard rammer, pulling the rammer in the sleeve to the maximum height and then allowing it to fall freely. Okay, so the position of rammer is changed each time to distribute the compactive energy evenly to the soil in this way. Okay, so each layer is racked with a spatula before placing fresh soil to provide a proper bond. There should be a proper bonding in the previous and the current layer or the next layer. So we are going to give the scratches, or we are going to give the racks to the with the help of spatula to the surface of a compacted soil. Then after that the collar is removed and the extra soil trimmed off to the top of the mold, and the weight of the mold obtained. So the weight of the soil is got by subtracting the weight of empty mold. Okay, so what we are going to do after trimming the extra soil from the mold, when we remove the collar which is present above the mold, when we remove the collar we will see that there is a presence of some extra soil above the mold. So we are going to trim it with the help of spatula or knife, and then we are going to take a weight of that particular mold. That will be weight of mold plus soil, and when we subtract the weight empty weight of a weight of empty mold, then we will get the weight of wet soil. Okay, then the bulk unit weight, that is gamma, of the soil is obtained by dividing the weight of soil by the volume of a soil, that is gamma is equal to V upon W. Okay, so with the help of this formula we can easily calculate the bulk unit weight of a soil, and a representative sample of a wet soil is taken and the moisture content is determined in the standard manner through oven drying. Okay, then the dry unit weight is obtained. Okay, we have a formula to calculate the dry unit weight, that is gamma D is equal to gamma upon 1 plus W. By using this formula the dry unit weight is obtained. Okay, then the soil is broken with hand and remixed with increased water so that the moisture content increases by 2 to 4% nearly. Okay, then the test is repeated with a least 6 different water contents. The weight of a soil itself gives an indication whether the number of readings is adequate or not, because it first increases with the increase in water content up to a certain value, and thereafter it starts decreasing. It decreases. Okay, so the test must be done such that this peak is established. Okay, so the moisture content dry density curve, that is nothing but the compaction curve, is drawn from the obtained values of dry density and respective moisture content or water content. Then the optimum moisture content and the corresponding maximum dry density or maximum dry unit weight are read off from the graph. Okay, so here we can see the graph. Okay, so the compactive effort or compactive energy transmitted to the soil is considered to be about 605 Newton meter per 1000 centimeter cube of a soil. So this test has been adopted as a standard test by the AASHO, that is American Association of State Highway Officials, initially. Then for coarse grained soils, an initial water content of 4%, and for fine grained soils a value of 10% are considered to be reasonable values, since the optimum value is likely to be more for later than that for the former. Okay, so this is about the standard Proctor test. Then we will discuss about the modified Proctor test. Okay, so this test was developed to deliver greater compactive effort with a view to simulating the heavier compaction required for the construction of airport pavements. Okay, so whenever we required the heavy compactive effort or heavy or greater compactive energy, then modified Proctor test is adopted. Okay, so the mold used is almost the same as that of the standard Proctor test, but with an effective height of 127 mm, and the weight of hammer is 25 Newton and the height of fall is 450 mm. Okay, initially we in the standard Proctor test the weight of hammer is 25 Newton and the height of fall is 300 mm, but here it is higher. Okay, so the mold is filled in 5 layers in modified Proctor test, each layer being compacted with 25 number of blows. But in modified, as we have discussed, the mold is filled in 3 layers with the 25 number of blows of compaction. The compactive energy delivered is of the order of 2726 Newton meter per 1000 centimeter cube of soil, which is about 4.5 times that of a standard Proctor test. And the moisture content dry density relationship, that is nothing but the compaction curve, may be obtained by adopting a similar procedure as in the previous case. Since the compactive effort is more for this test than for the standard Proctor test, the compaction curve in this case may be expected to lie higher when superimposed over the curve for the latter. So with the peak placed to the left. Okay, in the diagram we can see. Here we can see the curve for the standard Proctor test, and here we can see the compaction curve for the modified Proctor test. So here I have listed out the difference between the standard Proctor test and modified Proctor test. So we have seen the various laboratory tests, that is standard Proctor test and modified Proctor test. So there are various more laboratory tests are also there. I will give the names of those tests. That is Indian Standard Compaction Test, then Harvard Miniature Compaction Test, then Abbott's Compaction Test, Diator's test, then Jodhpur Mini Compactor Test. So these are also some laboratory tests, but among these the standard Proctor test or the modified Proctor test are the widely used for calculating the compaction parameters. Okay, so now we will discuss about the field compaction, that or we can call it as a in situ compaction. The construction of a saturated field usually consists of two distinct operations, that is placing and spreading in layers, and then compaction. So the first part assumes a greater significance in major jobs such as embankments and earth dams, where the soil to be used as a construction material has to be excavated from a suitable borrow area and transported to the work site. So in this phase, large earth moving equipment such as self-propelled scrappers, bulldozers, graders and trucks are widely employed. So the phase of compaction may be properly accomplished by the use of appropriate equipment for compaction. The thickness of layers that can be properly compacted is known to be related to the type of soil and method or equipment of compaction. So generally speaking, the granular soils can be adequately compacted in thicker layers than fine-grained soils and clays. Also, for a given soil type, the heavy compaction equipment is capable of compacting thicker layers than the light equipment. Although the principle of compaction in the field is relatively simple, it may turn out to be a complex process if the soil in the borrow area is not at a desired optimum moisture content for compaction. So the existing moisture content is to be determined and water added if necessary. The addition of water to the soil is normally done either during excavation or transport and nearly on the construction spot. So however, water must be added before excavation in the case of clay soils, and in case of soil has more moisture content than is required for proper compaction, it has to be air dried after excavation and compacted as soon as the desired moisture content is attained. So the soil compaction or densification can be achieved by different means such as tamping action, kneading action, vibration and impact. The compactors operating on the tamping, kneading and impact principle are effective in the case of cohesive soils, while those operating on the kneading, tamping and vibratory principle are effective in case of cohesionless soils. So we will see some of the methods of field compaction by using the smooth wheel rollers, pneumatic rubber tire rollers, sheep foot rollers and vibratory rollers. So first we will discuss about the smooth wheel rollers. So the smooth wheel roller, so this type imparts static compression to the soil. So there may be 2 or 3 large drums. If 3 drums are used, 2 large ones in the rear and 1 in the front is the common pattern. The compaction pressure are relatively low because of a large contact area. This type appears to be more suitable for compacting granular base courses and paving mixtures for highway and airfield work rather than for compacting earth fill. The relatively smooth surface obtained acts as a sort of a seal at the end of a day's work and drains off rainwater very well. The roller is self-propelled by a diesel engine and has a weight distribution that can be altered by the addition of blast to the rolls. The common weight is 80 kN to 100 kN, although the range may be as much as 10 kN to 200 kN. The pressure may be of the order of 300 Newton per linear centimeter of the width of rear rolls. The number of passes varies with the desired compaction. Usually 8 passes may be adequate to achieve the equivalent of a standard Proctor compaction. Next is a pneumatic tire rollers. So this type compacts primarily by kneading action. The usual form is a box or a container mounted on 2 axles to which pneumatic tired wheels are fitted. The front axle will have 1 wheel less than the rear, and the wheels are mounted in a staggered fashion so that the entire width between the extreme wheels is covered. The weight supplied by earth ballast or other material placed in the container may range from 120 kN to 450 kN, although an exceptionally heavy capacity of 2000 kN may be occasionally used. Some equipment is provided with a wheel effect, a design in which a slightly weaving path is tracked by the traveling wheels. This facilitates the exertion of a steady pressure on uneven ground, which is very useful in the initial stages of a fill. So here in this case, the weight of a roller as well as the contact pressure is an important parameter for the performance. The latter may be varied from 0.2 to 1 Newton per mm square through the adjustment of air pressure in the tires. Although this type has originated as a towed unit, self-propelled units are also available. The number of passes required is similar to that with the smooth wheel rollers, that is 8 number of passes to achieve the equivalent of standard Proctor compaction. So this type is suitable for compacting most types of soil and has particular advantages with the wet cohesive materials. Next is sheep foot rollers. Okay, so this type of roller consists of a hollow steel drum provided with projecting studs or feet. The compaction is achieved by the combination of tamping and kneading action. The drum can be filled with water or sand to provide and control the dead weight. As rolling is done, most of the roller weight is imposed through the projecting feet. So it is generally used as a towed assembly with the drums mounted either singly or in pairs. Self-propelled units are also available. The feet are usually either club-shaped or tapered. The number on a 50 kN roller ranging from 64 to 88. The contact pressure of the feet may range from 700 kN per meter square to 4200 kN per meter square, and weight per drum from 25 kN to 130 kN. So initially the projections sink into the loose soil and compact the soil near the lowest portion of the layer. In subsequent passes with the roller, the zone of compaction continues to rise until the surface is reached when the roller is said to walk out. So the length of studs, the contact area and the weight of roller are related to the roller performance. So this type of roller is found suitable for cohesive soils. It is unsuitable for granular soils as the studs tend to loosen these continuously, and the tendency of void formation is more in soils compacted with sheep foot rollers. Next is vibratory rollers or vibrators. So these are vibrating units of the out of balance weight type or the pulsating hydraulic type. Such a type is highly effective for cohesionless soils. Behind retaining walls where the soil is confined, the backfill much deeper in thickness may be effectively compacted by vibration type of compactors. A few of these types are nothing but vibrating drum, vibrating pneumatic tire, vibrating plate, vibro float, etc. So in this first part we have covered the meaning what is compaction. We have seen the definition of compaction. Then we have seen the various purposes of compacting a soil. Then we have discussed about the principle of compaction of a soil. Then we have seen the compaction curve. Then various terms related to compaction curve. Then we have seen the difference between the compaction and consolidation. Then we have seen the laboratory compaction test, field compaction tests. In the next part we will discuss about the factors affecting compaction, the effect of compaction on the soil, and various parameters. Okay, so if you like the content of this video, please subscribe to my channel and share this video with your friends. Thank you.